everyone. So this is our lecture, which we are going to upload in Box. So, and this topic is topological sorting. So let's look directly at the topic. So what's topological sorting? So topological sorting is also called ordering dependencies. We basically use this to order dependencies in some kind of relationships. For instance, given a directed graph G, where we have like age from U to V. So note that at first that we are given a directed graph and the ages are kind of like this. So from U to V. So what we want to make sure that we must do U or so these ages kind of mean some dependencies. For example, it's this is a course like CS220. You must take this before CS221, right? So this is a vertex in our graph. This is another vertex in our graph. And this age basically means is you must take 220 before 221. You must do this before you do this. So what we want is basically we can only do things one at a time. So we cannot do multiple things at a time. So in one semester, you have to take 220 and another you have to take 221. So we have to find a specific order so that the order of doing those work respects the dependencies. So the dependencies given, so we have to find such an order of the work so that matches or respects the dependency. So let's dig further. The topological sort is basically you are given a graph and you have to order the vertices. So at the end of the day, then you will say that yes, these are the order of vertices. So you have to do this first, this second, this third, and so on, so on, so forth. So where is it used? So this is used basically on multiple cases. So this is basically on like different cases. Just wait a minute. So yeah. So this is basically used in multiple cases. For example, compiling multiple files. So if you compile more than one file, like 5 or 6 files, you have to compile one thing first, and then the second, and then third. And it's possible that this depends on this file, this depends on this file. So you have to follow a specific order for compiling this file, right? So topological sorting is used in that. Even so, the example which I have just used, for example, do topological sort for graduating. Why? Because you take some course at first and some course next. So you have to find an appropriate order for taking courses so that the prerequisite requirements, the requirements like you have
it's 7 o'clock.
So prerequisite courses are taken before you can take the actual courses. So these kind of dependence and these kind of dependent ordering based on the dependencies is done by topological sorting. So for example, you are given this graph. So what we basically mean by topological sorting or topological ordering. Let's look at this. This graph, this is a graph actually given. So what we are saying here is you have to do 0 first and then 1. You have to do 0 first and then 2. So even 2 is dependent on 1 and 0. So for doing 2, you have to do first 0 and then 1 and so on and so forth. So what we want is we are given one graph like this. Our what we want is we want to linearly we want to like order our vertices in an order such that there are only so see these edges are these edges, right? So only you have one edge from 0 to 1. So this is the edge from 0 to 1. So see the edges are actually represented here. So this graph is basically represented in another version here. So here you can see that the vertices are kind of written one after another in such a way that the edges actually go from left to right. These edges only go from left to right. See again? No edge basically comes like backward. So if you have a backward edge, what does it mean? So you have to do 0 first, and then you basically what you do is you basically start the prerequisite for doing 1 and prerequisite for 2. So if you have a backward edge, like from right to left, then what it means, you have You will do some work in the future, but this part is prerequisite of 5, which you will do like in the earlier, right? So to do this work, you have to do this first, but you have planned to do this in future. So this actually doesn't hold, right? So topological order, basically topological sort is basically like ordering vertices in such a way so that all the edges go from left to right, left to right. All the edges go from left to right. So this is what we want to do after this lecture. So yes, again, the course requirements. See that this is a graph. So for doing CSE 143, you have to do map 156 first, CSE 142 first, and then CSE, after doing CSE 143, only then you can get 374 and 373. And finally, after doing 373, you can do 417, and 417 is a prerequisite of 374. So let's try to order these vertices such a way that the dependencies are met. So you can see that what we have done here is map 156. It's done first. So after you have done this, you have no no hindrance, no phase to do CSE 143 because the dependency is met. Then you will do 142, 143, 373, 374. But let's look here. So let's look this edge. This edge basically comes backward, right? So what we have said in the last slide, we cannot do this way. Why? Because if we have decided to do 374 first and then 417, but this edge basically tells us that we have to do 417 first. So the order we have shown here is not quite correct. So we cannot select courses on this order. Right? So now let's look. So for example, in this graph, can we find an order, or is it not possible to find an order? So we have to see that first before finding an actual order. So is it always possible to find an ordering so that it respects those dependencies? Let's see. For example, look at this figure. So yes, just look at this sum figure, for example. So you have see 373 first and 417, and then you can do like 374. So are you understanding? So 373 first, and then 417, 417, and then 374. So let's do 373 from this to this edge. Okay. The 417 has another edge to 374. We have given this, and this edge 373 to 374 we have given this. So in this representation of the same graph, so with the same vertices and with the same edges, all the edge go from left to right, left to right, and left to right. So this is a perfect topological order. So we have to do this first, and this, and then finally this. So this is so we can find the topological ordering in this graph. So tell me. But let's look at this graph. So see, 373 is a prerequisite of 417. 417 is a prerequisite of 374, and 374 is a prerequisite of 373. So see, here's we have found a cycle, right? So this is a circular dependency. 373 to 417, and 417 is then 417 has 374. But the problem is we have another edge that comes from right to left. So we have basically created a cycle. So you cannot do any course here. Why? Because if you want to do 374 first, you'll be asked, have you done 417? You'll say no. So if you want to go to 417 first, you'll be asked if you have done 373, and your answer will be no. So if you want to do 373 first, you'll be asked if you have done 374. So your answer will be no. You haven't started your semester yet, but you cannot start any course. Why? Because there's a cycle. So here you cannot find an ordering. So what's the problem? So this graph and the second graph basically has a cycle. So if you have a cycle in your graph, then it's not possible to find an ordering. Why? Because it will this will create some circular dependencies. It will depend on this, it will depend on this, and it will depend on this. So this is a circular dependency. So if your graph has a cycle, then you cannot not probably, then you can surely do not have any topological sort of that graph. So to find the topological ordering or topological sort of graph, your graph has to be directed, as I said before. For the first thing, your graph has to be directed. Why? Because direction basically means you have to do this first and this second. So without any direction, there is no such dependency, right? So this edge does not mean dependency. But if you give a directed edge, then it means a dependency. And you have to do this first and this second. So our graph has to be directed. And secondly, as I said, just be clear that it cannot have any cycle. So we have just shown this. So our graph needs to be directed. Our graph needs to be acyclic. What do we mean by acyclic? Which does not contain any cycle. So such a graph is basically called directed acyclic graph. Directed acyclic graph. In short, we basically say DAG. It's heavily used in graph theory. It's basically heavily used in algorithm class. So we give a short name for this. This is called DAG. So what's DAG? This is a directed graph, and this for surely doesn't have any cycle. Directed acyclic graph. So we need to have a directed acyclic graph to find the topological sort. So if you are given a graph and it has cycle, and you were say to find the topological sort of those vertices, first you will see that if it does have any cycle, you will say that it cannot have a topological sort. And only if it does not have any cycle, you go forward to the next procedure. So let's look at something more about this specific graph called DAG. So this is a DAG, right? So it does not have any cycle. But this was the first example that we had. So look carefully that a DAG will have one source vertex. What we mean by source vertex? Vertex that has no incoming edge. Vertex which does not have an incoming edge. So a DAG will have such a source vertex. If it does not have a source vertex, then it cannot be a DAG. Why? Because if every vertex has some outgoing edge and has some incoming edge, every vertex, if this is true for every vertex, then you can start at this vertex following some path, and you can always come back. So this basically creates a cycle. So to avoid a cycle, you have to have at least one vertex which does not have any incoming edge. You at least have to have one vertex which does not have an incoming edge. So another thing is the sink vertex. If a vertex that does not have any outgoing edge, we call it a sink vertex. Why? So, for example, if you see that if it does not have any outgoing edge, then it's called sink vertex. So its algebra is basically 0. So let's look at this graph. So let's look at this graph. So see, here we have one source vertex, and this is another source vertex because we have some outgoing edges here, but no incoming edge, right? This is the fact, so no incoming edge. So this vertex, this has some only incoming edges, but no outgoing edge, right? So if you have seen that clearly, then you can see that this is sink vertex, and these two vertices are basically source vertex. Why? Because it has only outgoing edges. This has only incoming edges. So a DAG must have at least one source vertex and at least one sink vertex. So otherwise, it's not possible to be a DAG. So a directed acyclic graph must have at least one source vertex. So let's look for it. So let's do topological sort, and the basic way. So at first, look that this graph is basically a directed acyclic graph. So now we want to do topological sorting. What we'll do first. So we have to find an ordering of vertices so that all the dependencies requirements are made. So if there is not an edge from x to y, if there's an edge from x to y, then we do x before we do y. So where do we begin? So what we are basically trying to say here is we have an edge like this, and we will do x first, and then we will do y. So which one will we will be doing at the very first? So if any vertex have outgoing edges and incoming edges, so if any vertex has incoming edges, then we cannot do it at the very first. Why? Because it must be done after something, right? So at the very first, we need to do something, we need to do some work which does not have any incoming edges. So this is not true for a source vertex, right? A source vertex only have outgoing edges, but no incoming edges. So this is a source vertex. So we first need to start at the source vertex. So we will try to find what are the source vertex here in this graph. So we have only one source vertex, which is CC 110, right? So we will start at this vertex. So look carefully. So after I have done CSE 110, so after I have done CSE 110, then the dependencies for these courses are met. So CSE 110 is a prerequisite for 215, 111, 221, and Math 112. After I have done this in the first semester, now I can do all this, right? So I'll remove these vertex from the graph and these dependencies. Why? Because I have done this course in the first semester. So after, one more time. So after removing this vertex, now what we'll do, we will do like CSE 1110. After doing 1110, we can do like 111. It doesn't depend on anything else, and no course depends on this. So we can do CSE 111. Like, so in the second, we have done CSE 111. So this vertex is done. Okay. So after I have done 1110, and then after I have done 111, so these courses are basically gone. So now, after removing those dependencies, now we will look for another source vertex. So after removing those dependent vertices, dependent edges, now we have one source vertex. Which one? This map 1.5. Why? Because it only has outgoing edges but no incoming edge. So now we will do map 215, right? So after doing map 215, we can do these courses. So these dependencies are no longer holding, right? So I have done map 215, so it doesn't hold. So after doing map 215, these two edges do not hold. Okay. So now I have only one source vertex, which is map 1125, because it has only outgoing edges, no incoming edge. So this basically after we have done map 112. Then I will do 220, and then finally I'll do 221. So if I do the courses in this order, so if I have 6 semesters, and at first I'll do 1110 and finally 221, then all the dependencies are basically met. So this is one way to do topological sorting. So what we are basically doing here is, so we first start the source vertex, we do this and remove this vertex and all the edges that are associated with this vertex. Then we will get another source vertex. We will keep doing the same. So we will get some source vertex at each state. We will do that. We will remove this vertex from the graph, and as long as we do not finish all the vertices. So, but this is not the way we will follow for topological sort. Why? Because we have done DFS, and just doing some minor nudge, we can transform a DFS to a topological sort. So finally, go to that destination. So we will do topological sorting via DFS. So we have seen this. So first thing that we will do is let's run DFS on this graph. Okay? So now, and then we will describe how this DFS can help us do a topological sort. So if you have followed the lecture of DFS, we have started here. So the starting time for this is 0. We are just starting. So then we can go from here to like where we will go. So we can go map 1 or 2. This is an H. Okay? So the starting time of this is 1. Then we can go from here starting time for this vertex is 2. Then from here we can go to here. The starting time of this vertex is 3. Then we cannot go from anywhere. From here we cannot go to anywhere. So you have to end here. The finish time is basically 4. So by doing this way, I've got all after running DFS, we have got starting time and finishing time for all the vertices, right? So this is the standard uses that we will follow. So let's look carefully. So let's look carefully about the finishing time, right? So we have done since 110 at the very first, right? So let's look at the finishing time of this vertex. This is the highest of all finishing time, right? And then we have done CC 111, it has finishing time 8. Then we have done map 215, if you remember correctly, and it has finishing time 10. Then we have done this, and finally. So let's look at these two vertices. We have done this first, and this has the maximum finishing time. We have done this last, and this has the minimum finishing time. So can we devise some relationship between finishing time and the order in which we do our tasks? So what we want is basically for every edge, if there is such an edge in our graph, dependency graph, we have to do this first, and then we will do this. Okay? So this is what we want. But to kind of understand what's happening here, let's look at how many kind of edges a DFS tree can have, right? So in a DFS tree, so in DFS, every edge can be of any of these four, right? So it can be pre-edge, it can be forward edge, it can be cross edge or back edge. So to know what these edges mean, you have to video just before. So it's called edge classification, and you have to know what this means before watching this video. Have you watched that? Jump back, watch that, and come back. So you can have pre-edge, forward edge, cross edge, and back edge. Each DFS can have these 4 kind of edges. So as we have said in topological ordering, we need to have a DAG. Otherwise, we cannot have topological sorting or topological ordering of the vertices. So if our graph is acyclic, then if the graph doesn't contain any cycle, then there is no back edge. So yes, again, if this is coming from the video just posted before. So this, if this is a DAG, then it cannot have a back edge. So we will only have these 3 kind of edges in our graph: pre-edge, forward edge, and cross edge. No back edge, meaning no cycle in our graph. Okay? So we have, if we have one edge, this will be either a pre-edge, forward edge, or cross edge. So what we claim is, in general, what we claim is if we have some edge of this sort from A to B, then our claim is what we have claimed before, that the finish time of A will be larger than the finish time of B. So for any edge A to B, the finish time of this will be greater than the finish time of this. So this is our claim. So let's look at why this happens. So to understand why this happens, let's go back to the DFS group. Okay? So to prove this, if there is an edge like from A to B, then what you must prove is the finishing time of B is always less than the finishing time of A. In other words, the finishing time of A will be greater than the finishing time of B. So suppose, yes, again, this graph cannot have any cycles. Okay? As we mentioned before, we are working on a DAG. So case 1 is either this edge is a pre-edge or a forward edge. What we mean by this? So these red edges are basically pre-edges, and these blue dots are basically forward edges. So if we have this edge and this is a pre-edge or forward edge, then we know from our DFS and the finishing time things that the starting time of this will start A at some point, and then gradually we will do this, and then we will start at B. Finally, we will finish at B. So starting time of A, then we will start B, then finally we will finish B, then at the very last we will finish A. So starting time of A and finishing time of A are here the two endpoints, and B will be started after A but will be finished before A. So A will start early and then B will start, then B will finish, and finally A will finish. Why? Because A is the parent of B. Okay? In this DFS tree, A is the parent of B. So A will start early and finish after B. So in that case, what happens is the finishing time of A obviously greater than the finishing time. So if this edge is a free edge or forward edge, this happens, that the finishing time of A is greater than the finishing time. So we are only left with another kind of edge. What that is, this is cross edge, right? So we have to prove that if this is a cross edge, again this holds that the finishing time of A is greater than the finishing time. We need not worry about the back edge. Why? Because in DAG, we will not have any back edge. We do not need to prove that it's a back edge. So for case 2, where A to B is a cross edge, let's look at this. So this is a cross edge, right? So we are working about this edge, and this is a cross edge. What we mean by cross edge? So this is an edge, but B was explored not by A. B was explored by some other vertex, and after exploring B, when we are exploring this A to B edge, we have already said that B is already explored, so we do not need this edge. So this is basically a cross edge. So if A to B is a cross edge, then what we claim is we must have explored B before A. Why? So what we are claiming is we have explored B first and then A. Why this happens? If we have explored A first, then we know that we have an edge from A to B, right? Then we know that we have an edge from A to B. If we have explored A first, then we would explore B via this way, via A, right? From A to B. And as we know that this did not happen. Why? Because this is a cross edge. So if it were a free edge, then I would say that A to B edge was taken in the free. But if it was not taken, it's taken as a cross edge, then we are sure that B is not visited via A. So B is visited via some other vertex. So if you have understood this correctly, then we can say that if we have visited A before, then we could surely visit from A to B. So we must have visited B, and then we have visited A. And this is only the reason that this edge A to B was not used in the tree as a tree edge and has been left out as a cross edge. So we have explored B first, and then we have explored A. So this is what I've said just now. So otherwise, we have gotten B from A. So A to B would be a tree edge. So if this is not a tree edge, if this is a cross edge, then we have surely explored B before A. So again, if we have explored B before A, then B was started early, B was finished early, and then after some time A started and A finished. So let's look at these two. The B was finished before A was finished. So the finishing time of B is less than the finishing time of A. So this is actually described here again. So B will start, B will finish, and then at some point of time A will start and A will finish. So we are interested in only these two values. The finishing time of B is less than the finishing time of B. So in all three cases, for tree age or forward age or cross age, we have got that the finishing time of B is less than the finishing time of A. So we have got what we want. So we have run DFS, and for all the edges, if there's an edge in our graph like this, it's a dependency edge, which will mean that we have to do A first and then B. After running DFS, what we get is the finishing time of this is less than the finishing time of A. So basically, the finishing time of A is greater than the finishing time. So after running the DFS, if we start doing things where the finishing time is higher, then we will always be doing the prerequisite task first and then the dependent. Okay? So what we want here is, if we come back to the topological sorting now, so in what order we should do tasks or take courses in the reverse order of finishing time. This is what we have to do. Again, for these kind of edges, the finishing time of this will be low and the finishing time of this will be high. So after running TFS, we have got starting time and finishing time. What we will do? We will do the task first, which has the highest finishing time, and then the second, and the third, and the fourth, and etc. Okay. So in this way, the CAC 110 has the highest finishing time, so we will do this first, and then we have MAP 215 has finishing time 10, so then we will do MAP 215, and then the next finishing time in from highest to lowest is CAC 111. So we will do this next. Finally, the next finishing time of MAP 112. We will do this in 221 as 220 and then 221. So this is the order we get. So we are basically doing nothing. We are just running the DFS. We are storing the finishing time, and after the DFS has been run, we will store the sort the vertices based on finishing time, and we will print the vertices based on finishing time, starting from the highest, ending with the lowest. So then we are done with topological sorting. So let's look at some of the key factors here. So look at this is the ordering that we have got in our earlier example where we were deleting vertices and the edges. We were deleting the source vertices and edges and then coming back to another source vertex. So this was one ordering that we have got following that algorithm. And after following our DFS algorithm, we have found this sorting. So this is one ordering of the courses. This is another possible ordering of the courses. And look closely that these page are not unique, right? See, the 221, 221 matches, 220, 220 matches, 112, 112 matches. But here we are doing MAP 215 first and then 111. And here we are doing 111 first and then we are doing MAP 215. Both are valid. Why? Because there is no dependency from 215 to 111. We can do 111 first and then 215, or we can do 215 and then 111. So what we are basically trying to say here is this is a valid topological ordering. This is also a valid topological. So both of them are valid. What we are trying to say here is that these topological ordering are not unique. So one graph can have multiple valid topological ordering, and you will be good if you find any of the value. You will basically be given full marks for any of the valid ordering you can provide. So what did we just learn? So DFS can help us in solving topological sorting problem. This is basically nothing. After finishing the DFS, you will just sort the vertices based on finishing time, and from highest to lowest, and then you get the topologically sorted order of vertices. So, and we have also seen that the thinking about the TFS tree is always helpful to understand what happens first and what happens next. So as a brushing up, as a final example, we will see this graph. So this is another graph, and we want to find a valid topological ordering for this graph. So we will start with this. Why? Because we have to do this first, right? Because it does not depend on anything else. So we will do A first, and after doing A, so this is as starting time 0. Then we can go from here to here. So starting time 1, then starting time 2, then starting time 3. So we cannot go anywhere from here. So we have to finish exploring these vertices, and the finishing time will be 4. So right after 3 comes 4. So the finishing time is 4. Our exploration for D is complete, and then we come back to this. Our exploration of T is also complete. Finishing time 5, finishing time 6, and finally finishing time 7. So what we have told here that we have to do the tasks in from highest to lowest finishing time. So A, the vertex A has the highest finishing time or living time, so we will do A first, and then we will do C, and then we will do B. Finally, we will do. So if we do in this order, if we do our tasks in this order, then we will basically respect all the dependencies, and we will not validate any dependencies, and we will be done. We'll be fine with our ordering. So thank you. I will be finishing this lecture.